We're going deep today, diving into the world of semiconductors,
Oh, cool.
the kind of unsung heroes of technology, wouldn't you say?
Yeah, definitely. Hidden, but so essential.
Like, I bet you, I mean, I have a bunch around me right now, but most people probably don't even realize it.
Right. They're in everything. Your
Yeah.
phone, your car, even your smart toaster probably has a few.
It's amazing, right?
Yeah.
So, to guide our deep dive today, we're using this really insightful research paper by Anastasiia Nosova, Semiconductor Industry, an overview,
Great paper.
and we're lucky enough to have, well, you, to help break it all down. So, welcome.
Thanks for having me. I'm excited to, try to make sense of this complex landscape. It's fascinating stuff once you start peeling back the layers.
Yeah, totally. So to start off, Nosova provides this helpful visual in her paper, Figure 1, which maps out what she calls the semiconductor value chain, basically. The journey of a chip from, like, an idea to a physical thing.
Right. It's like a flow chart almost.
Exactly, showing all the steps. And it highlights how specialized each step is, right?
Oh, absolutely. This isn't a one company show. It's a global ecosystem. We're talking different companies, different countries, all specializing in various parts of this process.
It's like a global relay race then, passing the baton, everyone with their specific skill.
Exactly. And you got to be fast, too, because this industry moves at lightning speed.
So true. So who are the main runners in this Silicon Relay team? Who should we know about?
Well, Nosova breaks it down into three primary categories. First, you've got your fabless companies like the Apples, the NVIDIAs, the Qualcomms of the world.
Okay, so the big names, the ones we hear about all the time.
Right, they're like the architects focused on designing these cutting-edge chips, but they don't actually manufacture them.
They leave that to someone else. Interesting. So they just focus on innovation.
Exactly, pushing the boundaries of what a chip can do, making it faster, more powerful, more efficient.
So who are these master manufacturers taking those designs from the digital world to, physical reality?
That's where the foundries come in, companies like TSMC. They're the artisans, the ones with the expertise, and honestly, the massive facilities needed to manufacture these chips at the scale we're talking about today.
It's mind-blowing, the scale. Like, how many transistors are we talking about on a single chip these days? Billions.
Billions, trillions even, all on a chip the size of your fingernail. The precision involved is just incredible.
It's insane. Okay, so we've got the designers and the builders, but you mentioned a third group, right? The ones who want to do it all.
Yes, the control freaks.
No.
Kidding, kind of. But yeah, the integrated device manufacturers, or IDMs for sure.
IDMs, got it.
These are companies like Intel, Samsung. They have the resources and the in-house know-how to handle both the design and the manufacturing themselves.
So it's like a more, what's the word, vertical approach. They control the whole process.
Exactly. It's a different strategy, gives them more control over their products, their timelines, everything.
Makes sense. Okay, so we've got our designers, our manufacturers, and our vertically integrated IDMs. But it can't just be them, right? There have to be other players, specialists behind the scene.
Oh, you're absolutely right. And that's actually a really important point because it highlights just how collaborative this industry is. Two other groups play vital, though often less visible, roles.
Let's hear about them. Spill the secrets.
Okay, so first we have the silicon IP providers. IP stands for intellectual property.
So they're like the patent holders.
In a way, yes. They develop and license pre-designed components, like little building blocks, that other companies can use in their chip designs.
So instead of everyone starting from scratch, you can license, say, a pre-designed graphics processing unit or a memory controller.
Precisely. Saves a ton of time and resources. It's like using pre-made Lego pieces instead of molding every single brick yourself.
Oh, I love that analogy. Makes total sense. So it's about efficiency, but also, I imagine, focusing on your company's secret sauce. What makes your chip unique?
100%. You got it. And that actually brings us to the other group I mentioned, which are absolutely crucial for this whole process.
Okay, lay it on me. Who else is part of this silicon ecosystem?
We can't forget the unsung heroes of chip design, the electronic design automation companies, or EDA companies for short.
EDA, okay. What do they do?
They create the specialized software that makes designing these incredibly complex chips even possible.
Wait, so without their software, it would be impossible?
Well, remember those billions of transistors we talked about? Imagine trying to design those circuits by hand. It would be like trying to map out every star in the Milky Way. by hand.
Okay, yeah, that's not happening.
Exactly. These EDA tools are like having a super-powered magnifying glass and a set of incredibly precise instruments. They allow engineers to manipulate matter at the atomic level, basically.
That's wild. So they're essential for what? Verification?
Yeah,
Making sure the chips actually work as intended.
exactly. They run simulations, test different scenarios, all virtually, before a single drop of silicon ever hits a wafer. It's much, much cheaper to catch an error in the digital world than after you've already built a million faulty chips.
Totally. So we've gone from the big picture, the different players, to now even talking about the tools they use. It's already so much more complex than I ever imagined, and we haven't even touched on how these chips are actually made.
Right, and that process, the journey from sand to silicon, it's even more mind-blowing, believe me.
Well, lucky for us, that's exactly where we're headed next.
Welcome back. Last time we met the key players, the designers, the builders, but now, like, how do you actually build a chip? It's kind of mind-blowing when you think about it.
It really is. I mean, you're going from silicon, like one of the most abundant elements on Earth, right, to this incredibly complex device that powers, well, everything.
It's true. So Nosova lays it out in her paper, the chip R&D process. Starts with, get this, chip architecture. So is that, like, are we talking blueprints here, like for a building? I like that analogy. Yeah, it's essentially the blueprint, but instead of, concrete and steel, we're talking transistors, interconnects.
Mm-hmm.
That's where they define how it functions, how it'll perform, what it'll prioritize, speed, efficiency, all of that.
Okay, so you've got the grand plan, the blueprint. What's next?
Verification. Got to make sure that blueprint is actually going to work.
Well, right, of course. Can't just, like, start building.
Imagine that. So yeah, they use simulations, all these sophisticated software tools, often from those EDA companies we mentioned.
Right, right. To catch any problems early on.
Exactly.
Yeah.
Much easier to fix it in the digital world than after you've, spent millions making a chip that doesn't work.
Yeah, no kidding. So even with a verified design, it's still not over, is it?
Nope. Gotta test it, like really put it through the ringer. And not just once, at multiple stages. Make sure it can handle everything you throw at it.
Because a chip in a phone, it's got to do a lot these days.
Oh, yeah. From streaming videos to running complex games, all without breaking a sweat.
Right. And she mentions CMOS, this, like, key technology.
Ah, yes, CMOS, complementary metal oxide semiconductor. It's like the workhorse of the industry.
The workhorse. Okay, so reliable.
Exactly. Been around for ages, super reliable, cost-effective. But even workhorses have their limits.
Interesting. So what are those limitations and, like, what's next? If CMOS is the workhorse, who are the thoroughbreds?
Good one. Well, as we pack more and more transistors onto a chip, things get tricky. That's where things like FinFET and GAA FET come into play. More sophisticated designs, to squeeze even more performance out of those tiny transistors.
So, like, squeezing more juice out of the silicon.
Basically, it's incredible what they're doing. But, we've talked about the design, the testing, the building blocks transistors, CMOS. But how do we get from a design on a computer to, like, an actual physical chip?
Yeah, that's what I want to know. It's like magic to me.
It kind of is. It all starts with a silicon wafer, this thin, super pure slice of silicon. And then it goes on this incredible journey of transformations, a bit like metamorphosis.
It does sound intense. So where do we start? What's the first step?
Well, Nosova actually visualizes it really well in her paper, Figure 4, if you want to take a look.
I am looking. Okay, so it looks like it all starts with deposition. So are we talking, like, geology here?
It's about building layers, but instead of sedimentary layers over millions of years, it's super precise layers of different materials, all serving a specific purpose in the final chip.
So carefully constructed, not random at all.
Not random at all. Each layer has a job to do. Then comes lithography, where the real magic happens.
Lasers, right?
Okay.
I knew lasers had to be involved somewhere.
You got it. Lithography is all about precision, shining light to etch intricate patterns onto the wafer. We're talking features smaller than the wavelength of light.
No way. That seems impossible.
It's mind-boggling, the level of precision involved.
Seriously.
Yeah.
So the lasers draw the blueprint, and then what?
Then comes the etching. They use chemicals, gases, all sorts of high-tech tools to selectively remove material, basically revealing the final structure of the chip.
Oh, wow, like carving a sculpture.
Exactly. And with all that layering and etching, you can imagine the surface gets a bit rough, right?
Yeah, makes sense.
That's where planarization comes in. It's basically a polishing step using chemical and mechanical processes to smooth everything out.
So it's all about precision. every step of the way.
Absolutely. And the machines they use for this, they're like something out of a science fiction movie.
I bet they have to be to achieve that level of, what do you call it, precision?
Exactly. Companies like ASML, they build these incredible machines, like their extreme ultraviolet lithography machines, EUV for short.
EUV, is that like a special type of laser?
Think of it as the most powerful, most precise laser you can imagine. They cost a fortune and are absolutely crucial for making those cutting-edge, tiny, powerful chips we see today.
It's amazing. From design to these incredible machines, it's mind-blowing how it all comes together. Welcome back to the show. I don't know about you, but my mind is officially blown.
The journey from sand to silicon is quite a ride, isn't it?
It really is. But even with all that we've uncovered about how these tiny chips are made, it feels like we're just scratching the surface.
Oh, absolutely. What's even more fascinating, in my opinion, is where this is all headed. The future of chip making.
And what a future it promises to be. So let's dive into those trends, shall we? What has you particularly excited or maybe even a little bit worried?
Well, one development that I find particularly fascinating, even a bit awe-inspiring, is the rise of AI in chip design.
We've talked about AI as a tool for verification, double-checking the work of human engineers.
Right, but it goes even further than that now. Imagine AI algorithms not just assisting, but actually designing chips, optimizing at a level we could only dream of.
So AI designing the brains of our devices. It's a bit meta, don't you think?
Absolutely, and the implications are huge. We could see a massive acceleration in innovation, more specialized chips, perhaps even a democratization of chip design itself.
Democratization, how so?
Well, if you remove the need for huge teams of engineers, the massive R&D budgets, it could potentially open the door for smaller companies, startups, even research institutions to design their own custom chips.
Wow, so it levels the playing field in a way.
Potentially, yes. But it's not all about AI. Another trend that's really shaking things up is the move towards what we call OEM custom silicon.
OEM custom silicon. Can you break that down for us?
Sure. So OEM stands for original equipment manufacturer. Think of companies like, well, Apple's a perfect example. Remember when they stopped using off-the-shelf chips and started designing their own for their iPhones and Macs?
Yeah, they made a big deal about it.
Exactly. That's OEM custom silicon. And we're going to see a lot more of that in the coming years. Companies realizing that to really push the boundaries of what their products can do, they need chips specifically tailored to their needs.
So instead of a one-size-fits-all chip, you have a chip perfectly optimized for, say, image processing in a smartphone or AI-powered features in a car.
Precisely. And that customization allows for incredible performance gains, efficiency improvements, things that just wouldn't be possible with a generic chip.
It's like the difference between, I don't know, buying a suit off the rack and having one tailor-made for you.
Perfect analogy.
So it seems like this silicon-powered future is going to be all about specialization, customization. But is there anything that worries you about this reliance on ever more powerful, ever more specialized chips?
That's a great question, and it brings us to one of the biggest challenges facing the industry, the limits of silicon itself.
We're hitting a wall.
In a way, yes. We can only make transistors so small, you know? We're approaching the size of atoms, and at that scale, quantum physics starts to interfere and things get a lot more unpredictable.
So Moore's law, this idea that computing power doubles every 2 years, it's dead.
Well, it's more accurate to say Moore's law is evolving. Silicon may be reaching its limits, but human ingenuity, not so much. Researchers are already exploring new materials like graphene, carbon nanotubes, things that could potentially outperform silicon in the future.
So instead of silicon chips, we might have graphene chips, diamond chips. It sounds like something out of a science fiction novel.
And that's what's so exciting about this field. What seems like science fiction today could be reality tomorrow. And beyond new materials, we have entirely new ways of computing emerging, like quantum computing. Who knows what the future holds?
It's true, the possibilities seem endless. This has been an incredible journey. We've explored the complex world of semiconductor design and manufacturing, met the key players, uncovered the trends shaping the future. It's amazing to think that something so small, so seemingly insignificant, plays such a huge role in our world today.
It's been my pleasure to join you on this deep dive. And to our listeners, I encourage you to keep asking questions. Stay curious. The world of semiconductors might be hidden, and it's a fascinating and incredibly important one.
I couldn't have said it better myself. So until next time, keep exploring.